Imagine you were trying to find a single, very specific clue in a 2-hour mystery movie.
Like a blink and you miss it kind of thing.
Yeah, exactly.
Yeah.
Say, like, the exact moment a suspect drops a key card. But instead of just watching the movie normally, you print out every single frame.
Oh, boy.
Right. All 170,000 of them.
Yeah.
You stack them in this massive, chaotic pile on your desk, and you try to look at all of them at the exact same time to find that one key card.
I mean, that would be completely unmanageable. You wouldn't just miss the clue. You'd probably, lose your mind in the process.
Yeah, it's a completely desk-breaking pile of photos. And the crazy thing is, that is exactly how modern artificial intelligence experiences the visual world right now.
It really is.
So welcome to the deep dive. Today, our mission is to decode this dense but incredibly fascinating technical article from MarkTech Post. It's about a new release from Alibaba's Tongyi lab.
Right. They released a framework called VimRAG.
VimRAG, exactly. And it promises to completely redesign how an AI remembers what it sees.
Which is, frankly, an overhaul the industry desperately needs right now. Because currently, AI is essentially drowning in its own visual history.
Okay, let's unpack this. Because, if you've played around with AI chatbots lately, you know they are getting incredibly good at reading text.
Oh, absolutely.
They use this framework called RAG, or Retrieval Augmented Generation. You give them a huge library of text documents, ask a question, and they just, fetch the exact right sentence. It feels like magic.
Yeah, it's very seamless for text.
But the moment you ask an AI to analyze a video or sift through 100 medical scans or, comb through dense visual documents, its brain just effectively breaks down.
What's fascinating here is the fundamental difference in how machines process text versus images. I mean, text is highly compressed human thought, right? It's naturally efficient. Visual data, on the other hand, is what researchers call token-heavy and semantically sparse.
Meaning there's just a lot of useless stuff in there.
Exactly. A single high-resolution image might cost the AI thousands of tokens to process. But relative to the specific question you're asking, maybe only 5 of those tokens actually matter.
That's a tiny fraction.
Yeah, the rest is just noise. Background pixels, shadows, irrelevant objects. So today we are exploring how VimRAG actually fixes this disparity.
But before we get to the solution, I think we really need to understand exactly how current AI is failing at these visual tasks. Because it's not just struggling a little bit, it's a systemic breakdown.
It really is. And to understand the failure, we kind of have to look at the standard operating procedure for AI agents today, which is this loop called REACT.
REACT, that stands for thought, action, observation, right?
Correct. Let's say you give an AI a complex task that requires multiple steps of reasoning. Under the REACT model, the AI just takes its entire history of thoughts, actions, and the visual observations it retrieved, and it just appends them into one constantly growing file.
It creates a linear, flat history. So, going back to our printed movie frames analogy, that means every time the AI takes a step and looks at a new scene, it prints out those new frames and just
adds them to the existing pile on the desk.
That sounds like a nightmare.
Mathematically it is. As the number of reasoning steps increases, the information density, which is the ratio of critical clues to total junk on that desk, it just plummets towards 0.
Because the pile gets too big.
Right. The vital visual clues are entirely drowned out by the noise of the accumulated history. The AI simply cannot parse the pile anymore.
So if I'm an AI engineer, right, looking at this desk-breaking pile of data, my very first instinct is going to be, hey, let's clean off the desk.
Right, pare it down.
Let's have the AI summarize what it saw, turn those bulky images into a short text description, and just throw the actual images away.
And that is the most natural, intuitive response. The industry actually calls it memory-based compression or iterative summarization. You maintain a stable information density because you are constantly compressing the bulky visual past into a compact text state. But, as the researchers at Tongyi Lab point out, this introduces a fatal new problem.
And they call this Markovian blindness.
Yes.
Which, by the way, Markovian blindness sounds like a sci-fi disease.
I mean, it functions like one for an AI agent. Because you've compressed the rich visual history into a brief text summary, the agent literally loses track of the fine details of what it has already searched for.
It forgets its own visual past.
Exactly. When you compress an image of a bustling room into the text phrase, say, check the kitchen, you lose the state of the room. Later, the AI might need to know if there was a knife on the counter, but the summary doesn't say.
Okay.
So in complex multi-hop scenarios, the AI gets stuck in repetitive loops. It searches the exact same places over and over because it can't remember the details of what it already looked at.
It's like a detective who writes, check the kitchen in their notebook, forgets what the kitchen actually looked like, and then just goes back to check the kitchen 5 more times, just to be sure.
That's a perfect way to put it. And in their pilot studies using a massive video corpus, the Tongyi lab team observed this exact behavior.
They actually saw it happening.
Yeah, they found that agents using text summarization suffered from state blindness just as badly as the agents trying to hold on to the massive linear history. Neither the hoarding approach nor the summarizing approach worked.
So if a linear memory grounds the AI in noise, and summarizing causes Markovian blindness, how did Alibaba's researchers figure out the right path forward?
Well, they ran highly targeted pilot studies to find the exact right trade-off. They tested 4 different cross-modality memory strategies to observe the statistical fallout of each.
Okay, let's break those down because the numbers here are really telling.
First, they tried just storing the raw visual tokens. This used a massive 15.8 thousand tokens on average.
Wow, okay.
And the accuracy was only 45.6% on image tasks and a dismal 30.4% on video tasks.
So the noise just overwhelmed the signal.
Exactly. Then they went to the other extreme, which is pre-captioning. This is turning everything into text right away before storing it.
Which is incredibly cheap from a processing standpoint, right?
Oh, very cheap. Only 0.9 thousand tokens. But the accuracy completely tanked. It dropped to 14.5% for images and 17.2% for video.
Wait, if text is so much easier for an AI to process, why not just use context-aware captioning to turn the image into text? Like, don't just blindly caption the image, but turn it into text based on the specific question you are trying to answer.
See, they actually tested exactly that scenario. Context-aware captioning did improve things significantly compared to blind captioning.
Okay.
It brought accuracy up to 52.8% on images, but it still fell short.
Why is that?
The underlying issue is that captioning, by its very nature, strips away fine-grained details. If you were trying to verify a specific, tiny fact, like the exact brand of a watch a suspect is wearing in a blurry video, a text caption that just says a man wearing a watch is completely useless.
Ah, I see.
You need the original visual data to verify facts.
Yeah, you can't cross-examine a summary. You need the original evidence.
Which led them to the winning strategy, semantically related visual memory.
Okay, what does that actually mean?
Instead of keeping all the raw pixels or compressing everything into text, the AI selectively retains only the specific vision tokens that are relevant to the query and discards the rest of the image.
Oh, so it keeps the important pixels and dumps the background.
Yes, and this used just 2.7 thousand tokens, so a fraction of the raw storage, but it hit 58.2% accuracy on images and 43.7% on video.
So it hit the sweet spot between retaining vital visual evidence and ditching the noise. Okay, so finding the right memory format, keeping the relevant pixels and tossing the rest solves the storage issue. But storing the data is only half the battle. How is the AI actually learning to use this selective memory?
Right, the training.
Because standard AI training relies heavily on trial and error, right? So what happens when it makes a mistake along the way?
Well, that question highlights a major standard training flaw, which their third pilot study actually exposed.
Oh, really?
Yeah. These models are typically trained using reinforcement learning, which rewards an AI based on the final outcome. If the AI gets the right answer at the end, the system gives a reward to the entire trajectory of steps it took to get there.
It's like giving a dog a treat because it eventually fetched the newspaper, even if it chewed up a slipper and chased a squirrel along the way.
The data backed up that exact analogy. The researchers found that in successful runs, roughly 80% of the intermediate steps the AI took actually contained noise or useless searches.
80%. That's huge.
Yeah. But because the final outcome was correct, the training algorithm was incorrectly rewarding that bad behavior.
Oh, I see.
Conversely, in failed runs, the AI might have executed a brilliant, highly valuable search early on, but because the final answer was wrong, that good search was penalized.
So it's learning all the wrong lessons.
Exactly. Any new framework needed to fix this fundamental training flaw to be successful.
So taking all these pilot discoveries, Alibaba's Tongyi lab built VimRAG with 3 core components to completely rebuild how the agent operates.
Yes, 3 main pillars.
Let's look at the foundational shift first, which is ditching the flat history entirely.
Right. Instead of a linear list of past actions, VimRAG replaces the interaction history with what they call a multimodal memory graph. specifically a dynamic directed acyclic graph, or DAG-GAG.
Okay, let's translate that concept into something a bit more tangible. Instead of a single straight timeline of events, the AI's memory is now a web, right? A branching map of thoughts.
That's a great way to visualize it. Instead of a rigid list, the AI builds a web of nodes. And each node in this graph is packed with context.
What kind of context?
Well, it contains local dependency info, meaning it knows exactly which previous thought led to this one, so the logic chain is preserved. It contains a subquery, which is a concise text summary of what it's doing. And most importantly, it contains a multimodal episodic memory bank.
And that memory bank is holding on to those highly curated visual tokens we talked about earlier.
Exactly. Because it operates as a graph, at any step, the AI policy can actively choose between three distinct actions. The first is RET, or retrieval.
Okay.
This is an exploratory action. The AI spawns a new node and executes a search to find new information in the visual documents or videos.
So it's branching out the web.
Yes. The second action is MEM, which stands for memory and multimodal perception, and this is incredibly vital.
Why is that?
This is where the AI takes the raw visual observations it just retrieved, applies a fine-grained semantic score, and distills them into those relevant visual tokens.
Ah, so it's doing the filtering right there.
Right. And for video, this step is remarkably powerful. VimRAG uses the temporal grounding capability of a model called Qwen3VL.
Okay, I've heard of that one.
Yeah, so instead of watching continuous motion and getting overwhelmed, the Qwen3VL model isolates specific, structurally important keyframes. It maps them to exact timestamps and compresses minutes of visual action into just a few vital tokens.
It's essentially creating a highly curated highlight reel on the fly before populating the node.
Exactly.
So it pauses its own search just to organize and curate its own memory. That's really cool. What is the final action?
The third is answer, or answer. This is the terminal projection. When the AI analyzes its web of nodes and calculates that it has gathered enough concrete evidence, it stops searching and delivers the final answer.
Okay, so it's actively curating its own memory, branching out this massive web of thoughts. But even a web can get too big, right? If the AI keeps spawning new search nodes, it's eventually going to hit a wall. How does it choose what to delete?
That's a great point. The researchers treated the AI's memory not as an infinite hard drive, but as a constrained resource allocation problem.
Okay, so there's a limit.
Yes, they gave the system a strict global token budget governed by a very specific mathematical formula, which is 5 times 256 times 32 times 32.
What do those numbers actually represent for the AI?
That math represents a strict computational cap. It means the framework processes up to 5 specific visual frames at any one time, allocating 256 tokens per frame, governed by a spatial resolution mapping of 32 by 32.
So it literally can't hoard data even if it wants to.
Right. By enforcing this hard limit, it forces the AI to prioritize what it remembers through graph-modulated visual memory encoding.
Wow, okay.
So to figure out what gets to stay within that budget, every visual item calculates an intrinsic energy score based on 3 factors.
Let's hear the 3 factors.
First, semantic priority, like how relevant is this specific image to the actual question being asked? Second, structural relevance. How many other nodes in the web are relying on this piece of evidence to inform their logic?
Okay, that makes sense.
And third, temporal decay. If a piece of evidence is old and hasn't been useful for several reasoning steps, its energy score drops. The system also utilizes recursive reinforcement.
What does that mean?
If an early node in the graph leads to highly successful downstream thoughts later on, that early node actually receives a boost in energy from its successor nodes.
Here's where it gets really interesting. I'm picturing, a classic detective string board on a wall.
Oh, sure.
You've got photos, newspaper clippings, red string connecting everything. This intrinsic energy score is basically deciding the physical size of the photos on the board.
That visual captures the mechanism perfectly.
Right, like if a photo is the cornerstone of the whole case, it has tons of red string attached to it linking to other clues, it gets a massive printout right in the center of the board. That covers structural relevance and recursive reinforcement.
Yeah.
But if there's an old photo from week 1 of the investigation that turned out to be a dead end, the detective takes it down to save space on the board for new evidence. That's temporal decay in action.
That dynamic allocation of resources is the precise mechanism that prevents the token bloat that usually kills linear models.
It's so elegant.
It is. And with the memory structured and budgeted, that brings us back to the training problem we uncovered earlier. The reinforcement learning flaw where the AI was being rewarded for making useless, noisy
Right,
searches.
the dog getting a treat for chewing the slipper.
Eh.
How does VimRAG train the AI to drop the bad habits?
They instituted graph-guided policy optimization, or GGPO. Because the agent's memory is now mapped as a transparent graph rather than a flat file, the training algorithm can trace the exact paths that led to the right answer and isolate the paths that were dead ends.
So it can selectively hand out the treats to the right steps.
Exactly. GGPO achieves this using a binary pruning mask during the training phase.
A pruning mask.
Yeah, so if the AI gets the right answer, representing a successful search trajectory, the algorithm looks at the graph and masks out all the dead-end nodes that weren't on the critical path.
Oh, wow.
It effectively hides them so that AI doesn't learn the bad habit of making those redundant searches again. It's like having a teacher go through your scratch paper after a math test and crossing out the dead-end calculations so you don't repeat them.
And what if it's a failed search? Does it still punish the whole attempt?
In a negative sample where the overall reward is 0, the algorithm still scans the entire graph. If it finds a step where the retrieval actually brought in valuable, relevant information, it applies a mask to save that specific step from being penalized.
That's incredibly smart.
Yeah, ablation studies confirmed this specific masking technique makes the AI learn much faster. It creates highly stable reward curves compared to baseline methods because the AI is finally getting clear, isolated feedback on every single action it takes.
So the architecture makes perfect sense on paper. The resource allocation is elegant. But how does this actually handle real-world chaos? When they put it to the test, what did the evaluations look like?
They subjected VimRAG to a massive evaluation matrix across 9 different benchmarks to test different types of reasoning. They used standard, rigorous benchmarks like Hotpot QA and Squad.
Those are notoriously difficult, aren't they?
Very, because they require multi-hop reasoning. The AI can't just find one fact. It has to retrieve a clue, understand it, use that clue to formulate a new search, and connect multiple different documents to get the answer.
So that tests the logic. What about the visual stress tests?
They used Slide VQA, which tests the AI's ability to pull highly specific facts out of dense, visually complex document slides, like charts and corporate presentations.
Oh, I hate reading those.
Right. But the real stress test was a brand new cross-video benchmark they built called XVBench. They constructed XVBench from the How to 100M dataset.
For context, How to 100M is a massive collection of instructional videos, right?
Yes. Think about how chaotic a standard internet tutorial video can be.
Oh, totally.
You have weird camera angles, sudden fast motion, skipping around the timeline, background clutter. To simulate that real-world chaos, they took all 9 of these benchmarks and merged them into a massive, unified corpus of approximately 200,000 items.
200,000.
Yeah, and these were interleaved, meaning text, images, and video were all mixed together in the same search space.
That's a lot to process.
It is. To handle that variety, they used GVE7B as the embedding model, essentially giving the AI a universal translator to convert all these different multimodal formats into a common language it could process.
That is an incredibly rigorous gauntlet. What were the actual scores?
Well, if we connect this to the bigger picture, the results represent a massive leap forward. Running on the Qwen 3 VL8B Instruct model, VimRAG achieved an overall score of 50.1 across the board.
Okay, 50.1.
Yeah, and the previous best baseline framework, a system called MEM1, only scored 43.6.
Oh, wow.
And on the specific visually dense benchmarks like Slide VQA, VimRAG hit 62.4 compared to MEM1's 55.7.
Those are significant jumps in accuracy. But for me, looking through the research, the most surprising fact in the whole paper wasn't just the accuracy score.
Yeah.
It was the computational efficiency. We talked earlier about VimRAG having 3 actions, and one of them is MEM, a dedicated perception step, where the AI actually pauses its search to extract keyframes and curate its own memory.
Right. From a traditional computer science perspective, you would naturally assume adding a dedicated step just for organizing memory would add significant time and computational length to the process.
Yeah, it sounds like it should slow everything down. But it didn't. VimRAG actually reduced the total trajectory length compared to the baseline model.
They really did.
Because it relies on a structured, graph-based memory, it doesn't suffer from Markovian blindness. It stops rereading the same things over and over. It stops executing invalid, repetitive searches. Taking a moment to organize its thoughts actually made it faster and leaner overall.
It completely eliminated the heavy tail of wasted token usage that plagues linear methods. It proves definitively that working smarter by structuring memory and dynamically budgeting resources is vastly superior to just trying to hold more raw data in a flat list.
So what does this all mean for you listening to this deep dive? Why should you care about dynamic directed acyclic graphs and intrinsic energy scores?
Oh, the application is huge.
Because we are rapidly moving into a world where we rely on AI to analyze vast, overwhelming amounts of visual data. Imagine an AI assisting a doctor by cross-referencing a patient's current MRI against a decade of previous scans, X-rays, and handwritten clinical notes.
Or an AI tasked with reviewing hundreds of hours of chaotic security footage across a dozen different cameras to find a single fleeting anomaly.
Exactly. If that AI relies on linear memory, it will drown in the pixel noise and hallucinate facts. If it uses basic text summarization, it will lose the fine details required to actually make a secure identification or an accurate medical diagnosis.
Yeah, VimRAG matters because it is a framework that finally respects the AI's own resource limits without losing the plot. It gives AI the vital ability to selectively remember what matters, forget what doesn't, and connect the dots across massive visual landscapes.
Well, that wraps up our exploration of Alibaba's Tongyi Lab and their groundbreaking VimRAG framework. Thank you for joining us on this deep dive into the future of multimodal AI memory.
Before we go, this research raises an important question, something for you to mull over. We spent this whole time talking about VimRAG, building a dynamic graph of visual memories. We explored how it decays older, less relevant information to save space through temporal decay. And we saw how it strengthens memories that lead to successful downstream thoughts through recursive reinforcement.
Yeah, it's a brilliant system.
But that isn't just an elegant computer science framework. It is remarkably, almost uncomfortably close to how human episodic memory and neuroplasticity actually function.
Oh, yeah.
Our human brains naturally prune the synapses we don't use and continuously reinforce the neural pathways that lead to successful outcomes. So if fixing an AI's memory problem requires mimicking the human brain's natural process of forgetting the noise and reinforcing the vital connections, what happens when an AI's memory architecture perfectly mirrors our own?